sklearn. Calibration. Calibration curve. Description. The calibration curve function in scikit-learn sklearn. Calibration. Calibration curve is a powerful tool for evaluating the reliability of probabilistic predictions from classification models. It essentially plots the true positive rate TPR against the predicted probability of being positive. This helps to assess how well the model's predicted probabilities align with the actual observed probabilities. Inputs. Why true? This is a 1D array containing the true labels of your data. The values in this array should correspond to the target variable you are trying to predict. For example, if you are classifying spam emails, this could contain values like spam or not spam. Ypred proba. This is a 2D array or a list of 1D arrays representing the predicted probabilities for each class. In the case of binary classification, each row would have two columns: the predicted probability of being in class 0 and the predicted probability of being in class 1. NBINS. This parameter determines the number of bins to use for creating the calibration curve. More bins generally offer a more fine-grained analysis, but too many bins might lead to noisy results. Strategy. This optional argument allows you to specify the binning strategy. The default strategy uniform creates bins of equal width. Alternatively, you can choose quantile to create bins with an equal number of samples in each. Outputs. Prob_true. This is a 1D array containing the average true probabilities for each bin. These represent the actual observed probabilities of positive samples within each bin. Probperd. This is a 1D array containing the average predicted probabilities for each bin. This represents the average probability assigned by the model to samples falling within that bin. Bin edges. This is a 1D array containing the bin edges, which define the boundaries between the bins used to create the calibration curve. Steps. Binning. The calibration curve function first divides the predicted probabilities into bins based on the chosen strategy, e.g., equal width or equal frequency. Averaging it then calculates the average true probability prob_true in the average predicted probability probperd for each bin. This averaging process is done separately for the positive and negative classes. Visualization. The function does not directly create the visualization. Instead, it provides you with the data prob_true, probperd, bin edges that you can then use to create a calibration plot. Metrics. Calibration error. This metric quantifies the difference between the predicted probabilities and the true probabilities. It's often expressed as a measure of the distance between the ideal diagonal line and pay. Calibration curve. A calibration error close to 0 indicates a well-calibrated model. Visualization plots. Calibration plot. This is a standard plot created by plotting prob_true against probperd. An ideal calibrated model would exhibit a straight line along the diagonal. Deviations from the diagonal indicate biases in the model's probability estimates. Fine-tune parameters. NBINS. Experiment with different values of NBINS to find the optimal balance between fine-grained analysis and potential noise. Strategy. Choosing the appropriate binning strategy, uniform or quantile, depends on your dataset and the specific characteristics of your model. Uncertainty methods. Confidence intervals. You can add confidence intervals to the calibration curve to assess the uncertainty associated with the estimated probabilities. Libraries like scikit-learn can assist in calculating these intervals. Challenges and fixes. Challenge 1. Challenge description. Inadequate binning can lead to a distorted calibration curve, making it difficult to accurately assess calibration. Sample use case. A model with a very skewed distribution of probabilities might require Non-uniform binning strategy to capture the variations effectively. Fixes. Adjust the NB-ins parameter to find a suitable balance. Experiment with the quantile strategy for binning, especially when dealing with skewed distributions. Challenge 2. Challenge description. The calibration curve might be overly sensitive to outliers in the data, leading to misleading interpretations. Sample use case. A few extreme cases with very high or very low predicted probabilities could disproportionately affect the overall calibration. Fixes. Consider applying outlier detection techniques to identify and potentially remove extreme data points. Explore robust binning methods that are less susceptible to outliers. Use a larger sample size to mitigate the impact of outliers on the calibration. Challenge 3. Challenge description. Overfitting can lead to a calibration curve that appears well calibrated on the training data but performs poorly on unseen data. Sample use case. A model trained on a small dataset might overfit the specific data points, resulting in unrealistic calibration estimates on new data. Fixes. Use cross-validation techniques to assess the model's calibration on unseen data. Implement regularization methods during training to prevent overfitting. Increase the size of your training data to reduce overfitting. Challenge 4. Challenge description. The calibration curve might not be informative for highly imbalanced data sets, where the minority class is poorly represented. Sample use case. In fraud detection, where fraudulent transactions are rare, the calibration curve might not provide meaningful insights due to the limited number of positive samples. Fixes. Use specialized calibration techniques designed for imbalanced datasets, such as the Platt scaling method. Consider using resampling methods to balance the dataset before training the model. Focus on evaluating the model's performance on the minority class to gain a better understanding of its calibration in that context.